Okay, got it? Yeah, good. So, of course, the Windows has accessibility support. You can, for example, change the colors, you can change the font size, but it wasn't good enough for her, so she still couldn't see the text. And what would have required, so what happens when you start increasing the font size is that then, of course, you would need to relay out the page, right? And that wasn't supported, even if already in the 1990s, there were AI methods like constrained programming that showed in principle how to do that. So it was really frustrating for me because I know it can be done relatively easily using the methods that we know, but it wasn't supporting my grandmother. And this is actually a big problem here, especially in Finland. There was an OECD report a year back that said that there's among the developed countries, we had the biggest digital divide between the young and the old. So the young people that we have are very good in using mobile devices and computers. The old people are almost doing nothing. And that's, of course, that has implications because we have quite high rate of digitalization. How well can you participate in the society? How well can you keep contact with your family? And how mobile are you going to be? And that has then implications to health and so on. So I thought that the artificial general intelligence mainstream view of AI wasn't really helping in this case. So most of the interfaces that we see are dumb, so they're not adapting to anything. They are done with this one size, one design fits all mentality, so they don't really adapt to anybody, and it's very costly to update them as well once the software systems are out. If there's any intelligence, it's mainly to monetize you, right? It's about advertisements and recommendations and so on, right? But it's not really helping people to use their computers better. So these are two bits of motivation why I didn't believe that this kind of natural language conversation is first of all possible, but also is not ethically what we should be doing. Also, the Finnish AI program puts the human in the middle. Well, you can think about these diagrams in many ways, but what we need essentially is some sort of human-centric AI. FKI has taken the role of doing AI that can naturally work with people, solve problems with people, demonstrates the ability to better understand people and their abilities, and aligns its objectives with us and supports us. So we're not the first to say that. I mean, there's whole centers dedicated to human-centric AI, for example, the Stanford High and all that. And the question is, well, what should that AI methodologically look like that is able to do this job? And I have disbelief in the, let's say, deep learning driven paradigm, and I'm going to talk about that. And we have developed in FKI an alternative to that bases more on theory and combines that with data-driven models in a new way. And just to draw this contrast more clearly, I want to launch a term that I came up with yesterday, and I call that artificial human understanding. And the goal in our program is machine intelligence that is capable of inferring reasons behind observed user behavior or human behavior, and also plan its actions in coordination with the user. And I'm going to open both of these terms, what they mean. So if you're going to compare side by side, what we're doing in artificial human understanding is to have intellectual capability for AI that allows it to interact and work with humans, as opposed to automating tasks or surpassing human capabilities in some tasks. It's a big difference in what we aim at. We also don't like to just have passive data set, have a benchmark data set and try to boost up the accuracy, but we need to test these systems in interactive settings with people. We're of course interested in, if you have a human understanding, is, well, how human-like is the behavior, and also how human likability, or how, what are the consequences of its behavior in interactive settings. Also, the scientific basis is different, right? As I'm going to show, my own background is in cognitive sciences, but we call for contributions from social sciences as well. And we look to have computational human sciences in a significant role in this paradigm. Now, even in the artificial intelligence community, there are significant doubts whether this will be the present paradigm will be sufficient for general intelligence. And I really like this quote: "Supervision is the opium of the AI researcher." And I think we need a richer approach to AI to solve the problems that I have been proposing. Well, some people still stick to the present paradigm, they just give it new names. Jan LeCun is talking about self-supervised learning, but I don't think it's intrinsically solving the problems that we want to solve, and I'm going to show you why. A little bit of history. I'm definitely not the first one to talk about these kind of goals. In my area, human-computer interaction and intelligent user interfaces, there's a history going back to 1970s, trying every possible method that AI research has developed, also in the context of interfaces, from logic to neural networks and probability. We summarized those things in a book last year, and now we have a follow-up book coming up. Now, why is it that nothing works of this? Let me give you a gallery of some thinking historically in this area. This guy is August Dvorak. He invented the Dvorak simplified keyboard. He didn't use any computational methods. What he did, he ran extensive studies of people typing, and then he started criticizing QWERTY keyboard that is not good for performance, ergonomics, nor learning. And then what he did, and he has a book called Typewriting Behavior that is very insightful. He started manually reorganizing the layout, and then he showed that his new keyboard layout is much better than the QWERTY layout. But there was the idea that we can take psychology, put it in the middle of design choices, and then improve the interfaces with that. However, they didn't have any algorithms to do that. If you go to the 1970s, there was interest from optimization community, especially operations research, toward interfaces, and they started with menus and keyboards, showing, for example, that the keyboard layout problem is an instance of the quadratic assignment problem, which is an NP-hard problem. And then, however, they didn't have any interest in actually solving those problems. They were intellectually interested in, okay, this is a class of that problem, okay, solved. Now we know how this works. Right? This is a QAP, therefore, we know this problem. However, because they didn't put in real input values to those models that they had about finger movement, for example, then none of these things were actually used. If you go to late 1970s and early 1980s, then people from cognitive science started to look at this, and they had this idea that, okay, we could build these cognitive architectures, and they're going to do all of this for us. Basically, if we have enough information about the person, what we can do is we can then use that as the basis of design and adaptation. However, there were two problems there. First of all, these models don't do any planning or optimization on their own, and those models are also out of reach in terms of computational complexity for the tools that they had at that time. So what happens is that they cannot plan with those models, they cannot optimize with those models, they cannot fit those models to data. Right? So they were just floating in the air. In the 1990s, there were attempts to relax those assumptions. Let's not put cognitive models in the loop. Let's have heuristics, and we can, for example, have rules that come from people's common knowledge of what works in interaction, and we can do rule-based and logic systems that are doing that. But those systems, and there was like 20 years of research on that is still alive, it turned out to be not scalable. So you do this very complex rule system, lots of specifications, and you basically over-engineer it for a particular case. And there's no way you can take that and then use it somewhere else. Now, who's going to be here? Everybody around 2014, when the deep nets came, said, okay, we're just going to treat it as a supervised learning problem, put in a lot of annotated data, we're going to have nice results. Well, all the fields, more or less, computer vision, natural language processing, and so on, started with the same idea. Okay, now it seems to work finally. Why don't we just crank it? Why don't we put it to DeepNet? Well, in the case of interfaces, it didn't work out. I mean, and there were very good attempts, even by Google, and our group also started looking at that. And then we quickly realized that it's not suitable for what we do. Well, one of the reasons is that it doesn't do, for example, it's not very good with discrete problems. If you have combinatorial type problems, this is a stochastic gradient method, right? That's one of them. But we're also going to talk about causality later. Okay, I want to introduce our program. This was the introduction. I'm going to introduce our program, basic ideas, then going to show some examples. Do you have any questions about our motivation for doing this thus far? Okay, so let's talk about our research program. It's not a research community, it's a research program.
No, but you said it correctly now.
Okay, good. Well, one of the inspirations is a pretty good paper by people from cognitive sciences and cognitive psychology called Creating or Building Machines That Think Like People, Think and Learn Like People. And this is from one of the top journals in this area called Behavioral and Brain Sciences. It's a mammoth paper, with the commentary from all the other authors who are important in this area, and then counter commentary from these authors. So it's really nice reading for the bus. And they were, taking the deep net-based approach and saying that, well, we're not going to have machines that think like people because they don't use causal models. They don't ground their learning into intuitive theories of physics and psychology. So when we reason about each other, we have models for intuitive physics models. We have intuitive psychology models that we use to make inference about your intentions and capabilities and so on. Well, where should that psychological knowledge come from? Of course, as you know, especially here in University of Helsinki, I think most of these areas are covered. There are many scientific understandings of people. If you think about psychology as a whole, and this is not even a full list, you go from very low-level things like physiology, neurology, and so on, to high-level things like cultural things. And many of those theories are expressed verbally or conceptually, so you cannot easily take them and put them into AI. Many of them, some of them are expressed mathematically, and some of them are expressed as simulations, as programs that you can run. We're particularly interested in using them as the basis of this getting computer to think like people. Now, what does understanding mean? I thought that since I talk about understanding, I should maybe say something about what I believe about that. And then I found two views prominent in the recent literature. Number one is more coming from sort of common sense, what we mean by understanding, and saying that if you say that you understand X, you can predict behavior of X in some new or unseen circumstances. You can infer causes that caused observed behavior of X from observation, behind observations. You can explain X in simpler terms, like you can say that, this rule governs the behavior of X. And maybe the hardest is that you could communicate knowledge about X to some other agent. And these are a pretty hard list, and I'm not claiming that we're even close to this. Judah Pearl has a nice book called The Book of Why, and he's arguing for this 3-level hierarchy of understanding, starting from statistical reasoning, going, for example, from a symptom to if you have an observation of a symptom, you go to inference about the underlying disease. Reasoning with interventions, and then counterfactual imagination. So if you have, what would happen, for example, if the weight of this was twofold, the weight of this thing, what would happen to my biomechanical control of this device? I mean, we never observe anything like that, right? But with models, right kind of models, we can do this counterfactual imagination. I think in interactive AI, and this is not a popular view, we're going to need causal models, especially for these reasons. It's because we need to go beyond the very skimpy human data that we have. For example, you may have big data, but the data about you in particular is often very, very slim. You need that to speculate in order to say that if I was to take this action, what would be the consequence on that person? And of course, I think this is coming back to the problem of adaptation, and how can you change something that, because every change to the interface or every change to a computing system will cause a reactive response from the user's perspective or human perspective, which means the human is a non-stationary objective function in a way, so it's learning all the time, right? So that makes it really hard. So we need to capture some aspects like that, so like learning and so on in these models. So purely data-driven approach is not giving you at the moment. So a little bit more about this speculation that I said. This is an interpretation of Judah Pearl's counterfactual imagination. So if AI takes this intervention, this action in a dialogue, or makes this design or adaptation, then this is what would happen to the human, right? So this is the human reaction on that. So this is the kind of capability that we look for. The better we can do that, the better our systems will be. Well, the way I frame this is, of course, done already, but in other engineering disciplines, especially many areas of, fluid dynamics or something like that. They engage in this kind of work, right? Maybe climate models are similar things. You can speculate with them. You can ask, well, what would happen if our CO2 emissions were halved, right? And see what's happening in the simulation. Well, we have to go back to the human, and then, of course, the areas of computational human modeling, they are old, but they're also relatively new in the sense that if you look at areas that call themselves computational X, where X is an area of human science, social science, then they're roughly like 10, 20 years old. And so there are areas in computational neuroscience, computational physiology, computational psychology, cognitive neuroscience, and so on. All these areas are covered that we need. But of course, the question is how mature those models are for our purposes. I think our interest in particular in making better interactive AI is in computable models of the human mind. And there are some criteria that you need for them. You need some input, some observations are regarding behavioral data, so what you can observe with your sensors. Number two, you need to be able to update that model to make a hypothesis about the causes behind the observed data, right, in terms of the individual that produced the data. And number three, the model has to be used somehow to guide the action of the artificial agent, for example, in terms of adaptation or optimization and so on. So these are requirements for computable models that we can use. Now, how do you get those models? Here's a continuum. This is a little bit of a stereotypical view, but let's say that here are your extreme data-driven approaches, like from neural networks. They are very data hungry, they are very intransparent, they generalize poorly, but then they have high representational power, so thanks to millions of parameters that you can have there. Then at the other end, you have something that is also difficult to deal with, which is the theoretical perspective. You take a theory from physics or medicine or psychology, you fully know what's happening there, but constructing these models is very hard. They're also less data hungry because they have stronger assumptions about what's happening. And what we like to do is something in the middle, and I'm going to talk about later, one shade of gray, if you will, where you have theory-driven models that come from here, come from psychology, come from cognitive sciences, and they have parameters, and these parameters are learned using ABC, for example, from data. But there's an alternative. You can also push the gray box toward the black box approach. For example, many artificial neural network solutions, for example, the self-playing AlphaGo AI, has innately built-in assumptions that come from human sciences. For example, that the Go is MCT, it's like a tree search thing. So that to me counts also as gray boxing in one sense. So what do you do with those models then? This is a loop that I use to describe this work to my colleagues and my students. People are living here in the user land. They're producing sort of data. We have inference. We update the model parameters. These models can be learned or they can come from theory. And then that's used as basis of optimization. And by saying optimization, I also mean planning. And then some intervention or design comes out. And so you want to do inference, you probably want to do something like experiment design. You want to choose which designs you put out in order to learn about the user. But you also want to drive the interface or the interventions based on your hypothesis on what's important for this particular user and what are the causal mechanisms behind the behavior. Well, if you do that, and I wanted to put up this slide because there was a recent paper called Machine Behavior. There was an idea that, okay, we're going to have social scientists study AI. And there was the idea that, the AI is already done. You learn from your data and you have your predictive model, and then we're just going to study the outcome, right? But I think we should not do that. We should do the opposite. We should integrate into our models assumptions that come from theory. And that means that then you need to seriously engage with those sciences. And it means that you have not only accuracy as important, but you also have values like the models being compatible with existing theories. Those models should be reproducing known empirical phenomena. So, for example, when we do models of, web navigation or menus, what we do is we list robust empirical phenomena. And typically, there's like between 5 and 10. Then we try to ensure that in simulations we can reproduce those phenomena, right? And of course, we want to ensure that our assumptions in the model are theoretically justifiable. it should also make some very verifiable predictions, and they should also be not too complex for inference and planning. Otherwise, you're going to have the same problem as the cognitive scientists had in the 1980s when their models were floating in the air. So now, putting all of that together, we're talking about a new type of machine intelligence that we programmatically want to build in FKI that brings behavioral and social sciences into the models that we use for interactive AI. And especially, let me open this up a little bit. What we're trying to do is we're trying to improve the efficiency and experience, these are very broad terms, of computer use by solving interaction problems algorithmically, where we use a subjective function, these computational models, some of which we can learn from data, or some parts of which we can learn from data, and then predict consequences of actions of people. So we can have human-like, artificial designer, or human-like tailor, who makes adaptations. Okay, a little bit more organizational words about what we do and who we are. So we are these active PIs, and this has grown organically. So we started with some meetings, and then these are PIs who are still with us. So we have weekly meetings, and we have science meetings, or we talk about results and research. And we have set as our objectives two objectives. First of all, we're interested in making human simulations, especially kinds of simulations that are reproducing human-like behavior. So not just, I don't know what's happening. In the sense that I said, we want to reproduce empirical phenomena. We want to be able to reproduce and explain individual user behavior. And these sub-objectives are selected based on who we are and what we do already. So we work on language, knowledge, eye-hand coordination, biomechanics, and so on. They could be something else, depending on if people came to work with us. What we try to do as a program, we also try to hire people who do this kind of basic research, human simulations, as well as software developers who could help mature up the level of software there. We also work on suitable machine learning methods, especially we'd like to work on inference, multitask learning, counterfactual reasoning, active learning, and so on. We are way more focused at the moment on the objective one, so doing the simulators, than this one. We're mainly now relying on existing solutions to these problems. But we'd like to work here. And I'll come back to some of the challenges that we're facing now in terms of these machine learning methods. Just to illustrate a little bit more the interest of the PIs who are involved, we collected this kind of list that, what kind of AI would you like to see in the future? We like to see an AI that, and these are application ideas, that boosts human reasoning capabilities, facilitates and boosts design work, or cognitive abilities, understands human conversation, and so on. We want to put, though, the focus on the simulations and the appropriate machine learning methods rather than the applications per se. But of course, these are best manifested or demonstrated via some applications, and need to be done like that. How we're organized, we have two meetings, meeting types. We have a weekly management meeting on Tuesdays at 2:30 p.m., and then we have a bi-weekly science meetings. For example, the next meeting we talk about movement models. How do we have models of human movement that solve problems? For example, how should you point, how should you walk, how should you climb, and stuff like that. That combine models of biomechanics with some machine learning methods. So if you're interested, just email me, and I can assign you to the list. Okay, let me then show a gallery. Some of them are done already, and some of them are ongoing. Perttu Hämäläinen is working, for example, on model-based interactive biomechanics. So you can think about a virtual avatar here solving problems like climbing, and that virtual avatar has human-like physiological bounds. For example, the movement ranges of joints, or in some work of his, he's looking at the forces that need to be produced by the joints. And in the future, he would like to go to musculoskeletal models that are also simulating the muscles. And underlying that, there's a development of his on continuous MCTs that is trying to solve the planning problem that the avatar is facing here. We also work on models of human visual system. This is an example of saliency modeling. This is a source. This is the original UI. And what you need to do is to predict eye tracking gaze patterns. So this is ground truth for us. We've been comparing and developing and parameterizing state-of-the-art models for mobile UIs, and you see that they are getting pretty well. There's pretty staggering progress from 1998. These are the first models of visual saliency toward where we are now. This is some of the best models in terms of predictive accuracy. This is a very much ongoing work that, for example, we're interested in doing generative models of some of the high-end areas of motor performance, such as typing, where you have very fast finger movements and that are coordinated, for example, and where also there are strong individual differences. Here we're going to use GANs. At this moment, these are recurrent neural networks that we're using. But basically what you can do is you can give a phrase and the hands will type that in a particular style that we can manipulate. What we can do when we have that model is then we can optimize, for example, keyboards, right? Or we can do adaptation of software layouts. We also work on a project that is related to the highlight that Arto is driving called Modeling Made Easy. Here, the part of understanding what we're developing here is understanding of the human as a statistician with biases. So we have a model of what kind of biases the human statistician has, and we try to infer that, and we're using it as a basis of proposing to a novice statistician modeling ideas. For example, that if you add this variable, this is what's going to happen to your model fitness. And here you see, for example, a scatter plot that shows collinearity or something like that. We try to do that in a way that is not steering the user too fast from the familiar part of the model space, but take these small steps in a controllable, understandable way. So we formulate it as a sequential planning problem using these models that are modeling the biases of the user. Here's something that we've been working for a while. We work on regular input devices. We try to make them better. If you know, when you use your mouse or touchpad, there's a thing called CD gain function. Different operating systems have different functions. Basically, they map the movement on your control surface to the movement of the cursor. And the question is, well, what would be the best CD gain function for you? So the velocity is mapped to the movement. And you have very different solutions by the commercial vendors. And why would you have to take this particular one? Why can't you have something that is custom tailored for you? And here, the type of understanding is coming from theories of motor control. And this is a speeded up thing of how we evolve or optimize the CD gain function. Basically, if you move your finger from here to here, trying to aim a button, that movement can be segmented into several sub-movements. And those sub-movements have different error characteristics, how much variance there is. This is actually inspired by work with Teemu earlier. Now, what we want to do with optimization, we want to suppress that variance in a way that then we have as little variance in the sub-movements as possible. And this seems to work really well, so we have very good results in this. So we can do that in the background. We just see your pointing movements, and then we parse it into sub-movements, and then do this kind of optimization under the hood, and just keep the results. One big thing that I wanted to mention is that machine learning has changed or is changing cognitive modeling itself. I'm going to use a term that I learned from Mika. The brain is just a bag of tricks. I don't know if you remember, but you said that. So there's many tricks that it uses for adapting its behavior to circumstances. From the way we move our eye gaze, or the way we attend to the environment, or remember things, and so on. And if you go to the old cognitive architectures, this is the kind of stuff that you may have seen about cognitive models. They didn't have any of that capability. Okay, so no adaptation at all. So these are infrastructures that are passive. Inputs go to outputs, and then something happens. So what they can do is they can, for example, represent the speed of your performance or the probability of error. But whenever you want to apply that, you need to design the way it does, with the way it solves the problem, the task at hand. Right? So it didn't have any capability of adapting itself. So what machine learning is bringing up now is a possibility of estimating how people adapt their behavior under bounds. This has roots in, economists, they started with utility maximization, and there was Herbert Simon with bounded rationality, and then there was bounded optimality, and now we talk about computational rationality. This is the latest term, where we use machine learning to estimate the strategies, how people adapt their behavior as a function of the environment, your own internal mechanisms, and your goals. And there are many ways you can do that. And this is where we converge with artificial intelligence. We're talking about reinforcement learning, Bayesian optimization, and so deep nets. Just to illustrate that quickly, this is an example of a strategy problem that you want to solve. Whenever we start with interaction analysis, we ask, well, what is the problem or task of the user? So for example, if you need to find the word politics from here, please raise your hand when you found it. So it's pretty small font. Okay, so Antti already found it. The thing is that I know exactly where it is, so it's very easy for me to spot it. It's over here, right? Because I gave this talk many times. But you didn't, right? So you have to engage in some strategy that relies on, for example, your foveated vision, peripheral vision, and choosing how do you sample, where do you move your gaze. So this is an illustration of the adaptive problems that we have all the time in interaction. And you can model those things, and this is something that we'll be working on in our group, as optimal recruitment of your cognitive capabilities. So let's assume that there are these cognitive architectures, we have different modules, we have different ways we can recruit those modules to solve a problem. Now, then the controller's problem is of how should you use them. And you can use, for example, utility learning or reinforcement learning to formulate a policy problem that we can then estimate. So now what's nice is that you can then train a model with a particular UI, you can make a change in the UI, and you can see, well, what are the consequences of that immediately and after practice, and you can get pretty interesting results that are compatible with human results. Another type of formalisms that we're looking at, sorry for the noise, is the Bayesian brain hypothesis. The idea is that we have strong priors that are governing our inference of the sensory signals that we're getting back. So we implemented a robotic finger that has human-like limited sensory modalities like proprioception, tactile perception, vision, audition. And now what the robot must do is to learn to press a button in such a way that it can predict its own sensations. And you can do that with Bayesian optimization. You can actually get pretty nice results that are matching the way humans press buttons. This seems very easy problem, but it's actually very hard. People press different buttons in different ways in terms of the velocities and the movement ranges and how precisely they can do that and how much effort they put into that. And with this very simple principle, you can get quite human-like results. So you can then change the goals. You can ask the robot, for example, to press the button more gently, or you can change the anatomy of the finger, or you can change the design of the button. And you just ask the robot to learn to press the button. Now we're trying to do the same with the pointing. So you have a laptop like here, and then you need to control the cursor to point at things and maybe later navigate in some hierarchies. It's way harder, but we're working on that. You can, I don't know if you remember these interfaces from the card reader, the predecessor, the present one. We've been working on using reinforcement learning to have a very simple and quick and dirty analysis of simple interactive tasks. So you basically say that I want to get from here to a state where I see this symbol, and then the reinforcement learning algorithm then solves the policy, but it has human-like bounds. So basically all the time costs are coming from a cognitive model. This has been very revolutionary for me because I started with these old cognitive architectures and they were sort of floating in the air. As I said, there was no way of inferring the parameters, and there was no easy way of using them because every time you use them, you have to predefine a script that says how you solve the problem. So now we can, for the first time, we can change the design programmatically, algorithmically, right? And then we can ask from this model, well, what's going to happen now? And this wasn't possible before. The other revolution is, of course, inference. Well, I discussed that last time I was here, how important that is. This is work with Jukka Korander and other ones where we would like to fit those models to data. For example, just to illustrate how difficult these are. I mean, if you have clickstream data, there are many interpretations to a single click. That can, was it a slip of the finger? Was it that you're exploring what this functionality is? Was it that you're really interested in that thing? So many possible explanations. So in a way, what we do with these models, we're playing this algorithmic Sherlock Holmes. So there's a click or a murder has happened. I need to trace back, well, what caused, who was the murderer, right? And here we use approximate Bayesian computation. We've been using that for a while, where you have this discrepancy minimization problem. If you think about this as all the behaviors that you can observe of a user, the user, well, actually has produced this vector here. You'd like to drive the simulator by changing its parameters programmatically. But the simulators are very costly if you think about learning these reinforcement learning parameters in every iteration that you do. Sometimes it takes a few seconds, but some of our simulators, they take days to learn those policies, right? So you have to be very sample efficient when you do that. For example, we've been looking at menu selection. The problem is that you're given a menu and you have to decide how you move your finger, how you move your eye. You need relative complexity to model even menu search with good results. But now the question is that if you have that model, how can you fit that to human data? And this is what we've been working on. So you, for example, have only click times. How long did it take for you to click an item? And you can then choose some parameters of the model. Let's say that you have human visual system related parameters. And then after you've done the inference, if the fit was good, what you can do is then you can use the model that you have learned, or the model that the parameters of which you have learned, you can then use to generate predictions for a completely unseen menu, right? And this is again very important for adapting or designing menus for individuals. But what's also nice is that you get these posterior estimations. Basically, you know how good your model fitting is. I mean, here you see that there's this kind of blob explaining the relationship between a posterior distribution for two variables. So you basically, if you take a point sample here, you know that you're not going to be representing the whole blob nicely, right? Because it's elongated like that. And what's also nice is that previously what we have been doing in this field is we've been manually tuning these parameters. So you take this model and then you try, well, would this work or would that work? Or you do grid search. And what we show in our work is that you can actually do that much better with ABC. This is very valuable for cognitive scientists. And we just this year we published a paper on how you can use ABC for cognitive models to improve the parameter fit. But what's nice is that you can follow this inference pipeline. You can take anything that has been mathematically or expressed in simulation in psychology, like anything like here. And then you can start fiddling around with that. And of course, because you get the posterior estimation, you can be a little bit safer that you're not over-interpreting the data. So we have some cases, for example, with Elisa, where we try to learn when their corporate users are getting lost on their site. So we're feeding navigation models to their data. Well, what's more valuable is that we also do what is called ability-based optimization. So we can generate and adapt interfaces for individual users. For example, we've been looking at how to do, and the model is actually running here. These are modeling workbench here. So you get finger and eye predictions for a person entering text. And what's nice is that those models are generative. They have parameters. We can either fit those parameters or empirically or just set them ourselves to simulate different types of users, people with tremor or dyslexia. And then we can optimize the interface for those user groups. So I started with this motivation of my grandmother, and this kind of thing can be now done. Okay, in the interest of time, just very quickly a couple of frontiers where we'd like to work more with you. There are many ABC-related challenges that are not only recognized by us, but there's a nice paper that came out recently, The Frontier of Simulation-Based Inference. And we're actually facing these similar things. When you have higher dimensional problems, it's not very sample efficient. When you're updating the model, the proxy model, then when you have lots of observations, it gets pretty tacky. How could you introduce human experts in the loop? And this paper is proposing, for example, combinations with deep networks that would be helping with these problems. But that's an interesting frontier where we can benefit a lot. I'd also like to engage with social scientists more. And there's a formulation of social intelligence, and there's a niche in social psychology that is very much compatible with us. This is a classic paper from Kantor and Kielström from UC Berkeley. And they talk about social intelligence as a problem. You have a particular social situation, and you have some goals, and basically it's very much compatible with the MDP and reinforcement learning type formulations that we are using in cognitive modeling. So I would be very interested in using these types of models. Okay, to summarize a little bit of time for discussion, we're looking at a new type of AI for understanding people that is able to anticipate the consequences of its action, can be reasoned with in human relatable terms. So it's not like a big blob of lots of parameters, but for example, it has structures and variables that we know what they mean. Can choose the designs or interventions that it does counterfactually, so it can speculate. It can learn and update itself in light of data, but does that in a conservative fashion, in the sense that then doesn't overinterpret the data, and so that we don't act when we should not act. And if there's any one single takeaway, it's this: that there's a lot of possibilities from psychology and cognitive sciences to be more heavily involved in AI research. It just needs to be compatible with that research. And this is my goal. Thank you.
There is now time for a quick question.
And this, please email me. You can join the meetings and the list. There's nothing secret about them.
Yeah. But is there a question in the audience?
Yes.
Yeah.
So have you looked about, like, okay, you present how to design good interfaces, okay, but we have current interfaces. Have you looked into the problem of transiting from bad interfaces to good interfaces? For example, I mean, probably Windows 8 has a better design interface than Windows 7, but everybody hates Windows 8.
Yeah, that's a core problem that we do. We've been looking at, for example, keyboards and layouts and menus from this perspective. What you need to model is the relearning. What happens when you change something? First you're going to, for example, look at the item in the wrong place, but then you have to reconfigure your search strategy. It poses an interesting problem, because then if you think about the cost of changing the interface, you could of course do a full whole change to the best interface that there is, right? But then then the learning cost will be even higher. People don't want to do that. So what we've been working on is how can you formulate it as a sequential problem. For example, take a step and avoid steps that would lead you too soon to an impasse, a bad interface. And for example, you can take a menu and you can start organizing it in single steps. People don't necessarily even notice that you're changing it, but you do subtle changes here and there. And over the time, you can lead it to a better interface. So one of the grand goals of understanding people in this context is understanding learning and relearning of things. And then we work with cognitive sciences to model it.
Okay. So, great. Thank you again.
Yeah.